All right, hello again, everyone. So today I'm going to talk about some matrix multiplication and matrix inverses. So in order to actually get an appreciation for matrix multiplication inverses, we should understand them both in terms of linear transformations, which is, after all, basically why they're developed. So let's start with matrix multiplication. Okay, so matrix multiplication. So as I said, this is used in linear transformations a lot. So as an example, to get an idea of what this is about, let's say the matrix A represents a reflection matrix. Let's say B represents, I don't know, let's say a rotation matrix. Then based on our understanding of linear transformations, the vector output AX should equal should represent the reflected x vector, and Bx represents the rotated x vector. Okay, so these are the outputs of the linear transformation. Now, if we have A being a reflection and B being a rotation, then suppose we were to compute AB times x or BA times x. So the first one, AB times x, would represent a reflection of the rotated x vector. So we're reflecting the already rotated vector, and BAX would be a rotation of the reflected x vector. In other words, if we were to have T of AB times x, is how you'd represent it, equals to AB times x, where AB is just a matrix, right? So it still follows the general form. This matrix here, B, would be the first transformation applied, and the A matrix is the second transformation applied. So the B would get applied to x first and then A. So in this case, it would be, as we said before, we would be rotating the x vector and then reflecting it. So that's why AB is a reflection of the rotated x vector. Okay. So enough of linear transformations here. Let's talk about some properties. So properties of matrix multiplication. There are actually quite a few properties. I'm just going to state a few really important ones, and we might be able to use that in a lot of our problems. So the first property is that I times A has to equal to A, and A times I has to equal to A, depending on, it doesn't, and so in other words, if you take the identity matrix and multiply by your matrix, it doesn't matter which side it's on, it will always equal your A matrix. Because in linear algebra, multiplying by I, the identity matrix, is really just like comparable to multiplying by 1 in algebra. It doesn't really do much. Now, okay, let's see. A second property here would be that A times BC is equal to AB times C. So in other words, it doesn't matter the order in which you multiply here, from left to right, as long as you follow this order here. So you can change up A times B first, or A times B times C first. It's commutative. The third property is that it is distributive. So if you have, by the way, A, B, C are all matrices here, you can distribute it here. A times B plus C is the same thing as AB times plus or minus AC. So it's distributive. And property 4 is that you can multiply any scalar by the matrix, and this should be the exact same as K times A first here times B, or A times KB. It doesn't matter if you multiply one of the matrices by a scalar, it won't change the overall product or the order. And then the fifth one, which is not so commonly used, but it's important to state, is that if you take the transpose, which is switching the rows and columns of the matrix product AB, you actually reverse the order. So it'd be B transpose times A transpose. And in general, the most important thing to remember here is that in general, AB does not equal BA. Now I said you can change the order in which you multiply, but you cannot switch the order. You cannot switch the A first or B first. It makes a difference. And if you're wondering why it makes a difference, think back to before where I said AB and BA, they each represented a different transformation, so they can't be equal. There's only very, very specific cases in which AB equals BA, but that's not a topic for this video. So in general, you cannot just say AB equals BA. That makes a big, big difference. Okay, so now let's just do a quick example of matrix multiplication. So let's take A equal to, I don't know, let's go like 3, 7, 2, 5. And we'll take B equals to 1, negative 1, 3, 2, 4, and negative 2. So if we want to compute the matrix product AB, let's first think of the dimension for what AB should be. So A here, this is 2 by 2. B here is 2 by 3. And so a 2 by 2 times a 2 by 3, we just look at the outer numbers, it should be a 2 by 3 matrix. I always think of the inner numbers as canceling, and you're left with the outer numbers as your dimensions of the matrix. It's just something to note here. So, okay, so let's actually compute the product here. So AB times AB would be 3, 7, 2, 5 times 1, negative 1, 3, 2, 4, negative 2. And so to do this, there's a very systematic and easy way to do this. You'll be ending up with a 2 by 3 matrix. And so the first entry of your new matrix, the AB matrix, the first row and first column is equal to the first row here with the dot product of the first column here. So this would be equal to 3 times 1 plus 7 times 2. Right, so you take the dot product of the vector 3, 7, dot product with 1, 2. This is our first row, and this is our first column. And this gives you the new AB matrix. It gives you the 1, 1 entry. Okay, and so that's the first entry. Now for the, let me just erase this real quick. And so to get the other entries, you just take the associative rows and columns. So to get the first row, second column entry of the new matrix, we take the first row here and multiply by the second column here. Take the dot product of the second column. So that would give us 3 times negative 1 plus 7 times 4. And then for the first row, third column, you take 3, 7, dot product with 3, negative 2. And so you get 3 times 3 plus 7 times negative 2. So that's our first row, or first, second, and third entries in the first row. And now for, let's say, the second row. Second row, first column would be 2, 5 dotted with 1, 2. So you'd get 2 times 1 plus 5 times 2. Now second row, second column would be 2, 5 dot product with negative 1, 4. So you'd get 2, negative 1 plus 5 times 4. And finally, the second row and third column would be 2 times 3 plus 5 times negative 2. And if you do the arithmetic here, you get the matrix 17, 12, 25, 18, negative 5, and 4. And this is our matrix product AB.